Okay, so we're going to talk about question 9 here, which is a little bit of a different type of one to what we've been doing. So let's have a little look at it. So to begin with, the first thing we need to think about is we're given, this is plutonium, okay? So plutonium-239 is a classic fissile material. That and uranium-235 are the most common ones. And you fire a neutron at it and it splits into 2 lower mass nuclei and 4 neutrons. Now the mass of the product is going to be less than the mass of the reactants, and that missing mass, that mass defect, will be converted into energy. The issue with this question is we're not given any of the masses. Now obviously you could look those atomic masses up, the masses of these isotopes up, but if you're given this in an exam situation, you're not going to be able to do that. So the question is, how do we answer this question? Well, we're given the binding energy per nucleon of each of the particles in this reaction, okay? So we're given the binding energy per nucleon of plutonium, strontium and barium, okay? And what we're going to do here now is figure out the amount of energy released in this reaction from this data, okay? So first of all, the first thing you need to do is work out the total binding energy on the left-hand side of the reaction, okay? So total binding energy on the left-hand side. Now we're given the binding energy per nucleon, but we need to work out the actual binding energy. Now, important to be aware that a neutron does not have any binding energy because it is a individual nucleon and it's not bound to anything else, therefore it has 0 binding energy. So let's figure out the total binding energy. So to do that, we're going to take the binding energy of the binding energy per nucleon, I should say, of plutonium, and we're going to multiply it by the number of nucleons to get the total binding energy on the left hand side. Remember, we don't need to worry about the neutron because it doesn't have any binding energy. If we were doing this in terms of mass, we would need to worry about the mass of the neutron, but not its binding energy, okay, because it doesn't have any. So 7.560341, and we're going to multiply that by 239. So let's work that out. 7.56, whoops, let's get that right, 7.560341 multiplied by 239 gives us 1806.9. Now, because this is to 7 significant figures, I'm going to make this to 7 significant figures as well. 1806.921, and that is MeV. Okay. Now we're then going to look at the total binding energy on the right hand side. Okay, so we've got the binding energy of the strontium and the barium to consider here. So it's going to be 8.521 580. That's the binding energy of strontium per nucleon. So we have to multiply that by the number of nucleons, which is 96. Okay, and then we have to add on to that the binding energy per nucleon of barium multiplied by the number of nucleons in barium. Okay, so that will give us our answer. So it's going to be 8.521 580 multiplied by 96 plus 8.35321. Oops, can't type this in properly. 210 multiplied by 140, and that gives us 1987. 1987.521 mega electron volts. Okay, so now that we've done that, we know that on this side the total binding energy is 1806.921, sorry, and on this side it's 1987.521 MeV, both of those. Okay, so you could already predict this because you can see that the binding energy per nucleon of plutonium is less than the binding energy per nucleon of each of the products. So what that tells you is, because the binding energy per nucleon, or the total binding energy, it doesn't matter which one you think of, let's just think about the total binding energy. Because the total binding energy per nucleon has gone up, that means that these nuclei must have given out energy, and therefore they are more stable. Okay, because remember, the binding energy per nucleon is the energy given out by the nucleus when it forms from its individual nucleons. So the binding energy has increased, and that means that these products are more, their nuclei, their nucleons in each of their nuclei are more tightly bound. They're in a lower energy state, a lower potential energy state, and they are more stable than the plutonium. Okay, and they've given out energy. Okay, so now we can work out the amount of energy released in this reaction. Okay, so let's do that. Okay, so energy released in reaction, now that's going to be equal to the final binding energy take away the initial binding energy. Okay, oops, 921, and that gives us 180 point, let's do that again, sorry, 180.600 MeV. Okay, if you do it on your calculator, you can just confirm that. It's 1987.521 minus 1806.921. That gives you 180.6 MeV. So that is the amount of energy released in this nuclear fission reaction. Okay, because you've got to get your head around this. Remember, the binding energy is not the energy possessed by the nucleus. It's the energy that's actually given out by the nucleus when it forms from its individual nucleons, or it's the energy required to pull the nucleons apart. So when the binding energy goes up, energy is released because the nuclei of the products have gone into a lower energy state. They've got less potential energy, they're more tightly bound, and therefore they have to have given out energy in order to enter that lower energy state. Okay, they're pulled together, they're experiencing a greater attractive force from the strong force compared to the original nucleus. They've moved up the binding energy per nucleon curve. If you were to draw the curve, okay, then they've gone from somewhere down here and they've moved up somewhere to around here. Okay, they've moved up the binding energy per nucleon curve. They're more stable. They've released this much energy. Okay, so that's example 9.